Okay, Assalamualaikum and hi. So we continue back to the chapter 1 part 4. Right, so in previous part we wanted to to derive the rate law for the reaction. So before we can derive the overall rate of reaction, we need to consider deriving the rate law for every step of the three important steps that I have already informed you in the previous part. Right, so in this chapter we will focus on adsorption, surface, and desorption, which is step 3, 4, and 5. All right. So now we go first on reviewing the adsorption part, which is step 3. Okay. So we have let's consider the first example of reaction, A producing B. So the adsorption on the surface would be A plus S, and then this is a reversible sign, A dot S. So adsorption is a reversible process, so we use a reversible sign. So okay, so let's go to your textbook to explain this one. Okay, so previously I have told you that okay, S stands for active site. Okay, so it's like your reactant A will go and attach on the active site. So once it attached, it will be A dot S. So let's go have a look on your textbook for this example. Alright, so let's consider carbon monoxide on metal surface as catalyst. So CO is the reactant and this is the catalyst active site. So it will be CO plus S, CO dot S. So it can be described using two model. One is as is a molecule, so it not detached. So carbon monoxide is absorbed as oxygen and carbon atom instead of molecular CO. So the second model is like this: CO plus 2S, it was C dot S and O dot S. So it's like balancing, like you do previously when you learn chemistry. It's like balancing your equation. So here you have 2S, right? So you need to put 2 in front of the S, all right? So 1C, 1C, 1O, and 1O. So this adsorption of carbon monoxide we can describe as in two models. One is carbon monoxide as a molecule, so it will absorb on the catalyst surface like this. But the second model, it can absorb as atomic. Okay, C dot S plus O dot S. Okay. So this the example for atomic is using ferrum. This one is using nickel. All right. So the former called molecular, and the second part, what we call it, non-dissociated adsorption. Okay. So let's consider the first model, which is CO adsorbed to the catalyst S as a molecular adsorption. Okay. So when we have this one, okay, wait, let me scroll. Okay. So we would like to derive a rate for every step in the mechanism. So now we are in the step adsorption step. So we wanted to derive a rate law for adsorption step. So how we can do that? So if you look here, okay, so A will go to the active site. Okay, so what is active site? I think, okay, I have here the definition of active site. Okay, active site is, okay, is a point on the surface that can form a strong chemical bond when absorbed atom or molecule. This is in your textbook. Okay, so let's say this is reactant A, this is your product B. So A will go to the active site and making the chemisorption. Right. So if you look here, CT, okay, stands actually for the total catalyst active site. Okay, so you can see there's a vacant, that this is the occupied site. So occupied by A, occupied by B. So CV is actually for vacant. So the total concentration of active site is actually CV plus CA dot S plus CB dot S. If you have C here, so it will be plus C dot S. Okay, right. So okay, so I go. Let's have a look on your textbook first. Okay, so how can we describe a rate law for the absorption part? Okay, so this is how it will be. So rate of attachment, so when we wanted to describe this part, is actually Ka. Okay, it's like you're deriving an elementary reaction rate when you learn in CRE 1. Okay, so Ka is actually your absorption constant. Okay, and then PCO is actually, because carbon monoxide is a gas, so gas phase, we describe it as in a pressure form. Okay, so that's why it's PCO. So PCO, all right, and CV. So the reactant will go to the vacant site. It will not occupy. It will not go to the occupied site. Okay, so that's why PCO times CV. So this is rate of attachment. Okay, since absorption is also is a reversible process, so that's why we have that reversible here. That's why we have this reversible sign, right? So this is this is to the right equation. So this is what we call it attachment. So to the left reaction, what we call it detachment. Okay, so the rate of detachment is actually being described by this thing. So you have the same reaction rate or absorption constant. Okay, so but it's in what you call it, is in opposite side. Okay, okay, so now we are talking about the detachment. So now the A is already attached on the catalyst surface. That's why it is no longer P, it's C. So we describe it as concentration of carbon monoxide or reactant that have attached on the catalyst surface. So the net rate of absorption is equal to, okay, we can write it as this one, or we make it simplify by having capital Ka, which is absorption equilibrium constant, okay, which is equals to Ka over K minus A. Okay, so this is actually the rate of absorption for carbon monoxide. Okay, so later you can try to do the one in the, okay, let's go to the one that in the example in the slide. Okay, right, so let's see here. So we have N-pentene the reaction of N-pentene producing I-pentene using alumina. So N-pentene is symbolized by N, I-pentene is I. Okay, so it was found that the rate law is this one. Okay, the final rate law would be this one. So normally we wanted to prove whether the rate law is similar as this one or not. Normally you will get a similar rate law. Okay, but however, in order for you to derive this overall rate law, you need to consider all the three steps: the absorption, surface reaction, and also desorption. Okay, we only have reviewed the absorption part. Okay, so for, let's say, for this absorption part of N producing I-pentene is actually is similar to the reaction that we have just now, the carbon monoxide or reactant A producing B. Okay, so N plus S is N dot S. So how are we going to describe the rate law for this step? So it's actually Ka Pn CV, because N is actually in a gas phase, right? So that's why P. If it is in liquid phase, we use C, right? And then CV is the vacant site, concentration of the vacant site. So this is Cn dot S. So detachment is from right to the left. So Cn dot S. So actually we have here is minus K negative A. But somehow K capital Kn is actually Kn over K minus N. So this is being simplified. Okay. Right, so that is absorption step. The next step is, okay, let's have a look in your textbook. Okay, the next step, okay, I skip this one first, okay. Let's have a look, before we go to the surface traction, let's have a look on the second model. Just now we have the molecular model, right? So this one is the one that have the second model, detachment, okay. So let's say the carbon monoxide will attach on the catalyst surface as C dot S and O dot S. How are we going to derive a rate law or for this absorption part? Okay, so if you look here, so we will do, okay, Ka PCO is the same thing, CV square. Why we do CV square? Because, okay, this part you need to have it correct. Okay, you need to balance it correctly because the rate that you derive here is based on the equation that you have here. So it's CV square because this the active site, you have 2 right in front here, so that's why it is square. Okay, so okay here, and then for the rate of detachment it's K minus A. Okay, so K minus A, you see here K minus A, so it will C dot S times C O dot S. Okay, right, understand? Okay, then you simplify it to this form where K capital A, capital KA is actually KA over K minus A. So that is example for absorption part. So let's have a look on the surface reaction part. Okay, this is the part where your reactant will be converted. Okay, so will be converted into B. So if you remember early in the previous slide, okay, so for surface reaction you will have either single site mechanism or dual site, okay, or sometimes you also may see some other like this is LE radial, okay, and also, okay, so in your case we only have 3, which is single site, dual site, and LE radial. So I will explain one by one of this step. Okay, for this part of chapter, this part 4, okay, I will describe the single site first. Okay, so for instance, so when, okay, it's a continuation from the absorption part. So we knew that A will absorb on the catalyst surface, then it will, in step 4, which is surface reaction, it will be converted to B dot S. Okay, so we would like to to derive a rate law for this one, for this step. So that's why it will be RS, okay, equals to KS. S is stands for surface reaction. So Ca dot S, okay, minus, because it is, it can be a reversible process, okay, because earlier the example is reversible, okay, minus Cb dot S, okay, and then over capital Ks. This is like similar to the absorption part, which is capital Ks is actually Ks over K minus S. Okay, so this is an example of single site. While in dual site, okay, it could be A dot S plus S, B dot S plus S. Okay, so the rate law that you will derive is this thing, is something like this, which is Ca dot S, okay, times Cv, because this is the vacant part. Okay, and then you will get Cb dot S times Cv, okay, because this is the vacant, so Cv, right? and also let's say you have, okay, so I think I stop here for this part, so we'll continue in part 5.